Hi, this is Andrew Villa, and I'm going to present my topical research presentation, Deepfakes, Generation and Detection. Introduction and background. It is almost second nature for mankind to feel the need to alter digital media in some way, shape, or form. Such abilities require inclusive proficiency and time-consuming dedication and effort, such as professionals working in Adobe Photoshop to edit photographs, or Adobe Lightroom to retouch said photos, as well as DAWs like Pro Tools and plugins like Autotune for single manipulation. In the domain of motion pictures, VFX is a common manipulation tool during post-processing. In some situations of visual media, re recreating animated faces with realistic facial muscle movements and expressions is desired with the use of high-speed tracking of markers such as in the movie The Avatar by James Cameron. The advancement of such technology used in the Avatar movie, among many others, has slowly evolved into what we refer to as deepfake technology. Deepfake, it originates from deep learning and fake. Deep learning as in the type of machine learning and AI that is a neural network with 3 or more layers that can learn from large amounts of data. It is a technique that can create and manipulate facial appearance, attributes, identity expression through deep generative approaches in which face images of a target person are superimposed onto a video of a source person to make a video of the target person appear to be doing and saying things the source person does. Deepfake technology is advancing fast, and its use is becoming effortless. Anyone can now produce a realistically looking face whose identity does not exist in the world or perform facial manipulation in a video with substantial realism. All it takes is an identity photo or short video of a target individual. Unfortunately, due to the ease of use and power of the technology, there has been a thin line drawn between good and evil when it comes to deepfake media generation. Depending on the content and its intended use, it can be easy to cross over. That is why deepfake malicious intent are a threat not only to public figures, but ordinary people as well. So continuing with the background, among the malicious use of deepfakes, there are violations to privacy and identity, like in 2017, a Reddit user applied deep learning to swap faces of celebrities into pornographic videos and was posting them online without consent. Other examples are security threats created from misrepresentation of politicians and world leaders, financial fraud from looming fake accounts on social media platforms, creating chaos in financial markets by creating fake news and false set-out images to confuse military analysts. When used in such a way, it can be a pressing and tangible threat to the integrity of media information available to us. Deepfakes are not only used for harmful reasons. As a matter of fact, there are positive uses of deepfakes and their applications in visual effects, digital avatars, Snapchat filters, creating voices of those who have lost theirs, or updating episodes of movies without reshooting them. There are also creative and productive impacts like realistic video dubbing of foreign films, creating scenes by joining two celebrities across geographic and generational boundaries, and education through reanimation of historical figures, as well as virtually trying on clothes while shopping. Following the events of increasing fake media, the subject of deepfakes gained traction in the academic community, and the technology has been rapidly advancing over the last few years. And here's a representation of that graph. And you can see that in 2016, there were no research papers on this topic, but by last year, 2021, it skyrocketed. And so we'll get into the topic of deepfake generation. And we'll talk about deep neural networks, autoencoders, GANs, creation process, deepfake classifications. And I will say that this topic is very complex, and I I did feel overwhelmed a lot when researching the topic. Um, but bear with me, there's a lot to go over. So here we go. So to understand how deepfakes are created and detected, we must first comprehend their foundational structures. For reference, a deep neural network is a series of algorithms that aims to recognize underlying relationships in a set of data through a process that imitates the way the human brain functions. Neural networks with multiple process layers are known as deep networks and are used for deep learning algorithms that can increase accuracy of machine learning models. So then deepfake applications are mostly developed based on deep learning techniques, which are known for their capability of representing complex and high dimensional data. There are several neural network architectures used to create deepfakes, such as encoder-decoder networks, generative adversarial networks, known as GANs, and there are subsets or subtypes of GANs, such as image-to-image translation, or known as pix-to-pix, cycle GAN, style GAN, etc. An encoder-decoder network is made up of a pair of two connected neural networks. So two connected, like the neural networks we just talked about. An encoder model and a decoder model that seeks to learn how to efficiently compress and encode data, then learns to reconstruct the data back from the reduced encoded representation to a representation that is as close to the original input as possible. Autoencoders are a type of encoder-decoder that are considered unsupervised learning. Although technically they are trained using supervised learning methods, they're referred to as self-supervised. Autoencoders, by design, they reduce the data dimensions by learning how to ignore the noise in the data. So to explain the process of the encoder decoders, so the encoder here is where the model learns how to reduce the input dimensions and compresses the input data into an encoded representation, which is the bottleneck. The bottleneck, which is the layer that contains the compressed representation of the input data. So the data starts off here, then goes through the encoder. Then the encoder sends the data to the bottleneck. So the bottleneck is the lowest possible dimension of the input data. After it's compressed by the bottleneck, then it's sent to the decoder. And the decoder is the model that learns how to reconstruct the data from the encoded representation to be as close to the original input as possible. And then it is sent to the reconstruction loss. And in the reconstruction loss, this is the method that measures how well the decoder is performing and how close the output is to the original input. Lastly, the training then involves using backpropagation in order to minimize the network's reconstruction loss. Backpropagation, or backward propagation of errors, is an algorithm that is designed to test for errors working back from output nodes to input nodes. Encoder decoders are used widely for dimensionality reduction and image audio compression. So like I said this before, but autoencoder was the first attempt at making deepfakes through Fake App. It was created by that Reddit user using a autoencoder decoder pairing structure. So for example, as illustrated, two networks using the same encoder, but different decoders, to see decoder A and B, for a training process. An image of face A is encoded with the common encoder and decoded with a decoder B. So you see down here, it's decoded with decoder B to create a deepfake. The reconstructed image in the bottom is the face B with the mouth shape of face A. Face B originally has the mouth of an upside down heart, as you can see here, while the reconstructed face B has the mouth of a conventional heart. This strategy enables the common encoder to find and learn the similarity between two sets of face images, which are relatively unchallenging because faces normally have similar features such as eyes, nose, mouth positions. This approach is applied to many deepfake applications such as Deepface Lab, Deepfaker, and Deepfake TF. Then another model that is used for deepfakes that is important to understand are the generative adversarial networks, the GANs. A traditional GAN model can learn how to model the input distribution by training two competing neural networks against each other, referred to as generator and discriminator. The generator creates fake samples with the aim of fooling the discriminator. The discriminator learns to differentiate between real samples and fake samples. Respectively, there is an adversarial loss used to train the discriminator and generator. The generator learns to create fake data by taking feedback from the discriminator. Feedback from the discriminator helps the generator to improve its output over time. It learns to make the discriminator classify its output as real. After training, the discriminator is discarded and the generator is used to generate content. When applied to imagery, this approach produces photorealistic images. So a different type of GAN is it's considered Pix2Pix is the type that it's called. So there are numerous variations and improvements of GANs, such as this one, image-to-image translation. So a basic GAN generates images from a random noise vector with no condition applied. A Pix2Pix image or image-to-image translation are translated from input to an output image conditioned on the input image through edge mapping. So an image is input to the generator network, which then outputs a translated version. The discriminator is a conditional discriminator, which is fed a real or fake image that has been conditioned on the same input image that was fed to the generator. The goal of the discriminator is to classify whether the pair of images is real from the dataset or fake. The final objective of the Pix2Pix GANs remains the same as all GANs. It too seeks to fool the discriminator such that the generator learns to translate images perfectly. And then we have the cycle GAN. So the cycle GAN is an improvement of the Pix2Pix that enables image translation through unpaired training. So with a Pix2Pix, you have to have paired training, paired images. So the network in this description forms a cycle consisting of two GANs used to convert images from one domain to another. Then back again to ensure consistency with a cycle consistency loss. So you see the forward consistency, backward consistency. A cycle GAN omits needing a pair of label. Cycle GAN omits needing a paired label by learning a map from X to Y and then forcing network to be able to construct input image, which means learning a map from Y to X. And this is the cycle and cycle GAN name. Paired data is harder to find in most domains and not even possible in some. The unsupervised training capabilities of CycleGAN are quite useful. So then lastly, for the GANs, we have the style GAN. It's a prominent method for faith synthesis based on a GAN model, motivated by style transfer with a special generator network architecture that is able to create realistic face images. So two networks constructed and linked together, source A and B, a mapping network and synthesis network consisting of several fully connected layers. So the output images are generated by copying a specified subset of styles source B and taking the rest from source A. Copying coarse styles from source B will generate images that have higher level aspects from source B and all colors, and finer features from source A. The generator architecture of StyleGAN can learn separation of high-level attributes, like the pose of somebody or the identity when trained on human faces. And it enables intuitive scale-specific control of the face synthesis. So here we have, let's move this. Here we have a summary of notable deepfake tools. There is a lot of them. So there's stuff such as, or apps such as Face Swap, which uses two encoder decoder pairs. Parameters of the encoder are shared. And then you have Face Swap GAN, adversarial loss and perceptual loss. VGG Face is the app that uses that. They're added to an autoencoder architecture. So it's essentially adding a GAN to an autoencoder. Few-shot face translation uses a pre-trained face recognition model to extract latent embeddings for GAN processing. Deep Face Lab expands from the face swap method with new models, supports multiple face extraction modes. Deepfaker is a DSSIM loss function, is used to reconstruct face. It's implemented based on Kara's library. Deepfake TF, similar to Deepfaker, but implemented based on TensorFlow. And I believe TensorFlow is a database. AvatarMe reconstructs 3D faces from arbitrary in the wild images. It gains reconstruction authentic, or no, it can reconstruct authentic 4K and 6K resolution, and so on. So yeah, Marionette, Disco Face Scan, Style Rig, Face Shifter, FSGAN, StyleGAN. Face to Face is a popular one. Real-time facial reenactment of molecular target video sequence, such as in YouTube videos, animates the facial expression of the target video by a source actor and re-render the manipulated output video in a photorealistic fashion. So moving on. Move this back. So in deepfake generation, there are classifications. So after discussing how deepfakes are made, we must go over the several categories of deepfakes to be able to differentiate them upon analysis. Various researchers have labeled the categories in a broad sense that places them into two classifications, such as lip sync or puppet master. Lip sync refers to videos that are modified to make the mouth movements consistent with an audio recording, and puppet master includes videos of a target person, the puppet, who is animated following the facial expressions and eye/head movements of another person sitting in front of the camera, the master. So then we have an alternative research that classifies deepfakes in more detail based on the specific manipulation of facial appearance. So such categories are identity swap, or face replacement, or face swap, replacing the face of one person with the face of another person, as you can see right here. Face replacement. Expression swap. The source is used to modify the expression, mouth, gaze, pose, or body of the target. Facial reenactment, same thing. And then attribution manipulation, or face editing, tampers with the soft biometrics by modifying some attributes of the face, such as the color of the hair or the skin, the gender, the age, adding glasses, etc., usually carried out through GANs such as the StarGAN approach, popular with Face app, mobile app. Entire face synthesis. This manipulation creates entire non-existent faces, usually through powerful generative adversarial networks through recent StyleGAN approach. In terms of popularity ranking measured by how often categories are tested by deepfake detectors, according to survey literature, the identity swap, which is the face replacement right here, ranks the highest for popularity, and the expression swap, which is facial reenactment, is the least attempted category. So the creation pipeline of deepfakes. Most reenactment and face swap networks follow some variation of this process. So you have your source passes through a pipeline that detects and crops the face. Then it extracts intermediate representation, like landmarks, boundaries, generates a new face based on some driving signal, another face, bends the generative face back into the target frame. So I probably meant to say blends the generated face. So another important thing to know is feature representation. Most deepfake architectures use some form of intermediate representation to capture and sometimes manipulate source and target facial structures, as well as pose and expression. One way to use the facial action coding system, one way is to use the facial action coding system and measure each of the face's taxonomized action units. Some use a UV map of the head or body to give the network a better understanding of the shape's orientation. So that's right here. 3 primary deepfake generalizations. One-to-one, a model that uses specific identity to drive a specific identity. Many-to-one, a model that uses any identity to drive a specific identity. Many-to-many, a model that uses any identity to drive any identity. And then if I move this, deepfake networks can be taught or developed to work with only a specific set of target and source identities. An identity agnostic model is sometimes hard to achieve due to correlations learned by the model between the source and the target during training. So next we have deepfake detection. First, we'll go through artifact-specific methods. Deepfakes generate artifacts that can easily be detected using machine learning and forensic analysis. Some methods identify deepfakes by searching for specific artifacts. There are 7 types of artifacts. So the type of artifacts that these are spatial artifacts, that are location-based artifacts that are seen in stationary media, like a still image or a paused video. So we have blending. Blending is artifacts that appear where their generated content is blended back into the frame. Researchers use edge detectors, quality measures, and frequency analysis. They train a CNN network to predict an image's blending boundary and a label, real or fake. And then we have the environment artifact, When the content of a fake face is abnormal in content to the rest of the frame, a method is used that contrasts the generated foreground to the untampered background using a patch and pair of CNN. Overflow from the face warping processes, lighting, and varying fidelity can indicate the presence of generated content. Then we have forensic artifacts, deepfakes detected by analyzing subtle features and patterns left by the model. So GANs leave unique fingerprints and show how it is possible the generator given the content, even amongst compression and noise. This is done by analyzing a camera's unique sensor noise, called photo response non-uniformity, PRNU, to detect past content. To find the residuals, a two-stream encoder-decoder is used to encode the color image in a frequency-enhanced version. The two encodings are then sent through an LSTM that categorizes the video based on a series of frames. Alternative methods have found that deepfakes tend to have inconsistent head poses. This results in deepfake detection by predicting and monitoring facial landmarks. This can be done by training classifiers to focus on imperfections by using a data set generated using a ProGAN instead of other GANs, because the images contain the least amount of frequency artifacts. So then we have temporal artifacts, which are time or sequence-based artifacts that are more visible while a video plays. So we have behavior artifacts. Due to large amounts of data on a target, mannerisms and other behavior can be monitored for anomalies. Behaviors can be used with no reference footage of the target. The method is to use a Siamese network. A Siamese network consists of two identical CNNs, each taking one of the two input images. The last layers of the two networks are then fed to a contrastive loss function, which calculates the similarity between the two images to detect inconsistencies in the recognized emotion taken from the clip's audio and video. Physiology artifacts. Some research was hypothesized that computer-generated faces can be identified by monitoring their heart rate. In terms of deepfakes, monitoring blood volume patterns under the skin. I think this is really cool. Likewise, another detection through physiology was done by monitoring irregular eye blinking patterns. What was found was that pulse signal helped determine the model used to create the deepfake. Synchronization artifacts. Inconsistencies have helped reveal that video dubbing attacks can be detected by correlating speech to landmarks around the mouth. This approach was improved by detecting when mouth shapes are inconsistent with spoken utterances. Coherent artifacts are realistic temporal coherence. That is, it's challenging to generate, and some authors capitalize on the resulting artifacts to detect the fake content, such as using RN to detect artifacts such as flickers and jitter, or uses an LSTM on the face region only, or refine the network's focus by monitoring the frame's optical flow, and use an LSTM to predict the next frame and expose deepfakes when the reconstruction error is high. So now we have undirected approaches. So an alternative focus of detection methods discards the focus of specific artifacts altogether and trains deep neural networks as generic classifiers instead to let the network decide which features to analyze. So we have classification, and which are DNNs have been shown to outperform traditional image forensic tools on compressed imagery. Standard CNN architectures can effectively detect deepfake videos. Methods of trained CNNs as a Siamese network using contrasting examples of real and fake images. Concerns of CNNs only make detections on data they trained. Cause for the use of hierarchical memory network (HMN) architecture, which considers the contents of the face and previously seen faces. Alternatively, a different method leverages the predictions of 7 deepfake CNNs by passing their predictions to a meta classifier. Doing so produces results that are more robust, fewer false positives than using any single model. Continuous testing revealed that a 3D CNN, which looks at multiple frames at once, outperforms both recurrent networks and the state-of-the-art ID3 architecture. Unfortunately, the use of classifiers to detect deepfakes is problematic since an attacker can evade detection via adversarial machine learning. So then we have anomaly detection. Unlike classification, anomaly models are trained on normal data and then they detect outliers during deployment. These methods do not make assumptions on how the attacks look and thus generalize better to unknown creation methods. This is done by measuring the neural activation of a face recognition network. The model is able to overcome noise and distortions by gaining a stronger signal compared to using raw signals, compared to using raw pixels. Sorry. So now I have some visual examples of deepfake detection. So in this example, we show the pre-processing method, a two-step process for face manipulation detection, where the pre-processing step aims to detect, crop, and align faces on a sequence of frames, and the second step distinguishes manipulated and authentic face images by combining convolution neural network and recurrent neural networks. So then we have another one, so this is the face classification stream that is used on GoogleNet to train the model on tampered and authentic images. Then the patch triplet stream is used to analyze features using steg analysis feature extractor and captures low-level camera characteristics and local noise residual. Here's another example of deepfake detection methods. So this is the schematic of the procedure of performance evaluation for the deepfake detection using image locals descriptors. And then down here, we have the research done where they use the heartbeat detection to identify deepfakes. I definitely would like to look into this one further, but did not know that was possible. Here's another one. So this one, a little bit more complex. The capsule network, it takes features obtained from the VGG19 network to distinguish fake images or videos from real ones. So the pre-processing step detects face region and scales it to the size of 128 by 128 before VGG19 is used to extract latent features for the capsule network, which comprises 3 primary capsules and 2 output capsules, or one for real and one for fake images. The statistical pooling constitutes an important part of capsule network that deals with forgery detection. Then we also have, so this one I found after my research. It is the expression manipulation detection. It's fairly new. It can both detect and localize specific regions within an image that have been altered. So the first and second columns show the original images and manipulated ones respectively. The black and white images in the third column are corresponding binary GT masks. Predicted masks in the fourth column, and generated cams in the fifth column for manipulated images from face-to-face and neural textures, the neural texture data sets. So face-to-face, that's where the images came from. So here's an overview of deepfake detection. So image features and textures consist of artifacts and fingerprints, inconsistencies of colors and distortion of textures, optical flow analysis, physical properties of camera, human features, and liveliness features consist of inconsistencies of head poses, unnatural eye blinks, biological signals, face warping, facial expression. Purely AI approaches consist of neural networks, end-to-end approaches, neuron coverage techniques, attention mechanisms, and incremental learning. I may not have gone over all of these, um, but I found this table after my initial research, and I liked how it spread everything out. And then here's another similar table of prominent deepfake detection methods. Not going to have to go over all of them. So you have eye blinking method. It explains the classifier technique and the technique LRCN. Key features uses LRCN to learn temporal patterns of eye blinking. Intraframe and temporal inconsistencies uses CNN and LTSM for classifiers, where CNN is employed to extract frame level features, which are distributed to LSTM to construct sequence descriptors useful for classification. It also tells you what kind of media it deals with, and then the data sets that are used. I thought this table was really cool. And so deepfake challenges. So there are challenges for both deepfakes or for both deepfake generating and deepfake detection. So for generating deepfakes, the challenges are current deepfakes result in a static performance due to being generated with a frontal pose. So there isn't much dynamics in the performance of deepfake generators, which, when not used maliciously, being able to create them with more than a frontal pose would be much better. Next generation of deepfakes will become increasingly more realistic with use of video to include expected expressions and mannerisms. The more real that deepfakes become, the more harmful their potential are. So then real-time deepfakes are enablers for phishing attacks. However, realism is not quite up to a believable standard yet. Realistic rendering of hair, teeth, tongue, and shadows, and the ability to render the target's hands, particularly when touching the face, is a big issue. Those tend to be very noticeable characteristics of deepfakes. And then the need for focus on effective countermeasures due to rapid rate of deepfake improvements. Deepfake improvements are happening a lot faster than the detection of deepfakes. And then for deepfake detection, access to large-scale, low-quality deepfake data sets affects deepfake detection negatively. So basically, even though there are large-scale data out there, a lot of the data is of low quality. And if we're going to teach these deepfake detection models to learn what to catch, to know what to look for, then we need higher quality data sets, because when we put them out there in the real world, they have a low accuracy because they're only being trained on low quality data sets. The binary classification system of media needs to become multimodal to include all the media's complexities. So the explainability of detection results. Interestingly, I read that the data results of deepfake detection are difficult for a lot of forensic experts to explain. So it's hard to be used as evidence in court because it's hard to explain to a jury, hard to explain to a judge, and a lot of forensic experts aren't specialized in like the algorithms and the whole process of deepfake generating and detection. Temporal consistencies among frames are not explicitly considered, and it necessitates to aggregate the scores over individual frames. And then social media laundering is detrimental to recover traces of underlying manipulation, and at the same time increases false positive detection. And then lastly, a challenge for both the perpetual competition of technology, know-hows, and skills between the forgery makers and digital media forensic researchers. That's a constant battleground between generating deepfakes and detecting deepfakes. And it's believed that the reason why detecting deepfakes is not up there with uh, generating deepfakes is because the data is not of the high quality it needs to be. Further research. So some further research would be anti-forensics with increasing effectiveness of deepfake detection methods. We also anticipate developments of corresponding anti-forensic measures which take advantage of the vulnerabilities of current deepfake detection methods to conceal revealing traces of deepfake videos. So more further research to address the threat of face swapping technology or deepfakes. The United States Defense Advanced Research Projects Agency, DARPA, initiated a research scheme in media forensics to accelerate the development of fake digital visual media detection methods. Recently, Facebook teamed up with Microsoft and the partnership of AI Coalition to launch the Deepfake Detection Challenge to catalyze more research and development in detecting and preventing deepfakes from being used to mislead viewers. Another research direction is to integrate detection methods into distribution platforms such as social media to increase its effectiveness in dealing with widespread impacts of deepfakes. The screening or filtering mechanism using effective detection methods can implement on these platforms to ease the deepfake detection. Watermarking tools can also be integrated into devices that people use to make digital content to create immutable metadata for storing original details such as time and location of multimedia contents, as well as their untampered attestments. Watermarking integration is complex and difficult to achieve, and it has been talked about using blockchaining. Blockchaining has been used effectively in many areas, and there are very few studies so far addressing the deepfake detection problems based on this technology. As it can create a chain of unique, unchangeable blocks of metadata, it is a great tool for digital provenance solution. So my own personal research, firstly, I would like to educate myself more on algorithms and machine learning, whether through online courses or videos. This will help me get a better understanding of the process and models used to create decent deepfakes. Another area of research I'm interested in is the use of deepfake detection applications that are used as prevention measures for social media platforms and how these models are constructed and its success rate. Lastly, I'm interested in researching further into the detection method that measures the small periodic changes in skin color of a person in a video caused by blood flowing through their face, known as remote visual photo trying to say that, known as remote visual photo it's known as PGG. Yeah, where they can detect changes in color of skin based on the blood flow through their face, kind of like the heart rate detection. So additional resources, I have links to the DARPA media forensic program. I have a link to this elaborately designed interactive diagram that shows that allows researchers to explore their own interests on popular deepfake generation or detectors. I have a link to the Facebook Microsoft partnership coalition, and then an article that references the focus on current challenges and next steps for deepfakes. That was taken from my references on some of the other articles. An interesting website of examples of entire face synthesis. This one's cool, where every time you refresh the page, a new image of an unreal person is created, and they look freakishly real. And then I have, if you're interested, a link for beginners in deepfake machine learning to learn what GANs are. So then I have this cool deepfake information trust chart, whether to tell between hoax, entertainment, propaganda, or if it can be trusted. And then here's some other interesting charts. And my works cited. All right, that's all I have. Thank you for watching. I hope you enjoyed it.